Hi everyone, welcome to another video. In this video, I'll be going and doing a deep dive into AIML engineering concepts, just basic concepts and high level details that I need to speak out loud and revise for myself. So that's what I'm gonna do. I'm trying to shoot this because this will help me reflect back onto the answers that I gave and how convincing it is to someone when I try to explain the concepts. So, just to get a feedback and see where I am in my preparation journey, this will really be helpful, I feel. So, I'm gonna make a small Google Doc as well as interact with AI tools to understand where I stand in the situation right now and see how it goes further. So I'll be sharing my screen in a while and I'll be most probably practicing by giving it a job description, extracting the important keywords from it, and then practicing each keywords and answer flows related to that. So I'll be sharing my screen. So I'm using Gemini as of now, and I'll quickly check if it's visible already or not. Like my screen, if it's visible or not. Yeah, it is. So what I did right now is I gave it a prompt of a job description with the qualifications and responsibilities, and I'll ask it to extract all the exact keywords, tech and non-tech, in this job description and make a table for me to study. Make sure include everything. Classify it into most important, good to know in the table by prioritization of study. 3 hours at every concept. Okay, so let's see. I'm using Gemini. And do I have any tools? No, because I'm using it in cognitive. So let's see if it's able to grasp that. Okay, so as you can see, it gave me the keyword metrics. These are the technical keywords which are like most important. These are the non-technical keywords or domain keywords. These are important and this is good to know. So I'm gonna revise according to this. I'm gonna prioritize what's most important right now, then move on to the other sections of it. So let's see, it created a study guide for me. says that you could go to core architecture in the first hour, focus on multi-agent orchestration RAG, where multiple agents like maybe LangGraph perform specific tasks. So we need to understand the difference between a simple Lang chain, which just has like maybe one graph or one agent, and a cyclic graph, which is LangGraph, which will allow us for loops. So we need to study the difference between Lang chain and LangGraph. Next is deployment environment like AWS Government Cloud or Azure ILF5. I have no idea on what this is. Even these are like new for me. I have studied LangGraph before, but I don't think I've studied LangChain. So this is something new. We need to study some security, government data protocols, and impact. Okay, then data and performance, high signal training data sets, ontologies. Oh wow, this is a new term for me. An ontology in AI is a formal way of naming and defining the types, the relationships. Okay, and then so okay. So what I'm gonna do is I'm gonna start with LLMs first. So okay, I cannot give me all necessary important questions and answers to revise for this role, medium and advanced level on LLMs. Give 50 question and answer with star format and relevant real world examples or features. Okay, let's see. And on the side, I'm gonna make a Google Doc as well. I'm gonna do okay. This is also incognito. Okay. Study revision lamps. Here are 50 revision question and answer categorized by complexity. Each uses a categorized star style: situation, task, action, result, logic, or a direct technical explanation. So, what I'm gonna do is I'm gonna read the question and then try to speak out the answer loud, and also see if I can find an image or check. Make it more detailed and longer than this and better. basics of LLM, middle, then move to the middle level, and then to the hard level. Get 50 questions. Okay, this is much better, I think. Alright, so what I'm gonna do is I'm gonna copy this and paste it in my Google Doc. So let's read it and understand what the questions are about. So the level 1 is foundations or the basics, and the focus is on transformer architecture, tokenization, and basic prompting. So let's see transformer architecture. So when it comes to transformer architecture, we have input. The input is converted to embeddings, and then it goes to the decoder layer. And the output is then again fed back to the decoder, I think. But let's have a quick read, speed read. What is transformer architecture and how it works? Okay. The transformer architecture uses self-attention and parallel processing, multi-head attention, positional encoding. It has traditional models for RNN and LSTMs, but this transformer has self-attention mechanism that will use parallelization for improved performance. It was first introduced in Attention is All You Need by Vaswani in 2017. It eliminates the need of recurrence by using self-attention and positional encoding, making it highly effective for sequence-to-sequence tasks such as language translation or text generation. So this is a diagram. Let's see what are the essential components. First is layer normalization. So normalization activations reduce covariant shifts. Self-attention mechanism is about query key value and scale dot product, where user will enter a query and get an answer, I think. uh, Next is multi-head attention mechanism, syntax focus, semantics focus. We have residual connections, which bypasses layer and allows only necessary layers to go through. It will improve gradient flow. We have positional encoding such as sine function, cosine function, and feed forward layers called fully connected layers and activation function. So let's read about it. What is self-attention? The self-attention mechanism allows the model to consider all words in a sequence, like converting words into numeric maybe, focusing on the most relevant ones regardless of its position. Unlike sequential RNNs, it processes the relationship between all words at once. So each word we have is represented through query, key, and value matrices. And relevance between each of the word is calculated using scale dot product formula using softmax. For example, if the sentence is the cat sat on the mat, cat might strongly attend to sat rather than mat just because it is nearby to it. And there is a dot product happening between each of the product, I think. So this is self-attention. Okay, positional encoding. Since transformers do not process input sequentially, positional encoding preserves word order by adding positional information to the word embeddings. This encoding uses sine and cosine functions. Okay. Uh, Position encoding formula. to use sine and cosine positional encodings to encode the embeddings as per their positions. So if the word it is present in two separate sentences, their embeddings will be different for both sentences due to added positional encoding. Alright, I got a little bit of idea, not that much. It's not entirely clear to me right now, but I will move on. Um, Without this encoding, sentences like he ate the apple and the apple ate he would appear identical. But because we are doing the sine and cosine formula, it's making sure that the word ate, even though it is in both of these sentences, its positional encoding is different. So they are both the sentences are different. Let's read about multi-head attention. So multi-head attention appears like this feature applies self-attention multiple times in parallel, with each attention head learning different linguistic pattern. Some heads might focus on subject-verb relationships, while others will capture the semantics, that is meaning. So if we have a sentence, each of the sentence will have its syntax as well as semantic. So our model is able to capture both of them parallelly. And in the end, we combine the syntax output and the semantic output both to get a unified representation. Now, talking about feed forward layers, each of the transformer block contains feed forward neural networks that process attention outputs. This consists of two fully connected layers with an activation function with this formula, and these layers enhance feature representation. Let's have a look on how they look like. So we can see this is input layer, then hidden layer 1, hidden layer 2, and output layer. And this is the flow of information. Each of this has a weight attached to it, an input attached to it, as well as bias. So this will be weight wx1 s1 and goes to different layers. It does not have any loops or feedbacks and is used for pattern recognition. Layer normalization stabilizes training by normalizing activation functions across features, which reduces internal covariate shifts and improves convergence speed. During training, this normalization prevents sudden changes in feature magnitudes, making the learning process more consistent. So, when we want to stabilize our activation function across features, so there are many different keywords. Let's see. Layer normalization. Stabilize the training process and improve performance. This is batch normalization, layer normalization, instance normalization, group normalization. I think this explains it better. If we have input, feature, and batch, and our images of pixels with channels and batch, CNN, this would be layer normalization is say CNN, whereas in transformer, it's gonna be like this. a technique that normalizes activations within each transformer layer to stabilize training and improve gradient flow through a model's many attention and feed forward blocks. So if this is the pre-layer, we have different layers. Input is layer norm, which goes to multi-head self-attention. To addition, layer normalization, feed forward. So output from addition is going to the addition. Okay, but this article is kind of different. It says you don't need transfer normalization in transformer anymore. We generally like to keep the magnitude of inputs, weights, biases, outputs, etc. between 0 and 1. Neural networks just same mathematically. Layer normalization helps avoid this by rescaling weights to be between certain range. In doing so, you can generally keep the things stable without interfering with training too much. You usually see this implemented as a layer of network which takes input of the previous layer and outputs the scaled weights. So there is rescaling happening and we are making sure that the weights are between certain range. Okay. What is covariate shift and convergence speed? Covariate shift is when statistical properties of your input data changes between different stages of training or inference. Change in distribution of new network activation due to updated network parameters during training. Corresponding distribution of input data changes between training and testing phases while the conditional distribution of input remains unchanged. It is done by changes in data distribution as parameters, weights, and biases are updated. The distribution of output from each layer changes. These changes propagate through the network, altering the outputs to subsequent layers and causing each layer to encounter different distributions of inputs over time. This continuous shift in data distribution complicates the training process, as each layer has to adapt to these evolving inputs. Example of scenarios causing changes in data distribution: batch training. When we train data with mini batches, each batch or fold can have a slightly different distribution of data. As the network learns from these batches, the activation distribution of neurons change, leading to covariant shift. Data augmentation. Applying various data augmentation techniques such as rotation, clipping, scaling can alter the distribution of input data. Learning rate adjustment. Adjusting the learning rate during training can cause significant changes in the weight updates. A higher learning rate might lead to larger weight updates, causing more shifts in data distribution. So we can say learning rate is directly proportional to weight updates in this case. Okay. During training, the model parameters are iteratively adjusted based on the gradients computed from the loss function. This updates cause changes in the activation of neurons in each layer. As these activations shift, the subsequent layers receive inputs with different statistical properties, creating a moving target. Poor weight initialization can cause extreme shifts in activation distribution in early stages of training. The use of nonlinear activation functions such as ReLU or sigmoid can amplify shifts in data distribution. Uh, as weights are updated, outputs of these activation functions can change dramatically. Different optimization algorithms such as SGD, ADAM, or RMS prop have unique behaviors in how they update weights. This can also be different from each other, and that is why there is the shift which is happening. This leads to slower convergence, as each layer must continuously readjust to the changing input distribution, which can lead to slower convergence rate. Training instability. The fluctuating distribution can cause training instability, where the model oscillates between different states rather than steadily progressing towards the optimal solution. So it's really hard to find the stable set of inputs that will minimize the loss functions and have a great accuracy. There is also problem of vanishing and exploding gradient. So vanishing and exploding gradients is basically when the model during backpropagation, the gradients, if they become really small or very large, it's very hard to update the network weights properly. So vanishing and exploding gradients. In vanishing gradient, the weights of model may become zero while training. The weights near the output layer show significant changes, while the weights near output layer may show. Oh, this is the same thing, I think. The model learns very slowly. The model may stop learning just after a few epochs. Weights of model may become NA, not a number, while training. The weights of model grow exponentially. The model may show huge changes in loss. So as we move to the layers from input to the output, the vanishing gradient becomes less, reaches zero. Exploding gradient goes NA and not a number. The presence of vanishing gradient problem basically occurs due to extensive usage of sigmoid. The presence of exploding gradient occurs due to extensive usage of ReLU activation function. Okay. Poor generalization. Because of the shift, it's the model struggle to generalize well to new data. Okay. How do we address this problem? By patch normalization. Normalizes input of each layer in a neural network to have a mean of 0 and variance of 1 during each mini batch training. This is done by introducing two new parameters, scale and shift, for each mini batch, allowing the network to learn an optimal normalization for the activations. Hmm. Wait, I have just been sharing one screen so far. I'm gonna make this video again. Okay, let me delete this video and then make it again. No, actually leave it. We'll just share my entire screen. I just realized that I was just sharing one screen. I thought I was reading everything. Let me share it again. So, uh, these are the questions that I copied from Gemini just to practice. But on the side, I was like basically reading from this article on internal covariance shift problem in deep learning. This is a article. So I was on this on how to address the internal covariance shift. One method is to try batch normalization, which will normalize the input of each layer. It has parameter scale and shift, and in each mini batch, we are allowing the network to learn an optimal normalization. Batch normalization stabilizes the learning process by reducing the internal covariance shift. It enables fast convergence and use of higher learning rates. Next would be adaptive learning rate, as it adjusts the learning rate for each parameter dynamically based on the history. We could use AdaGrad, RMS Prop, or ADAM. And adaptive learning rates help mitigate internal covariance shift by making the training process more resilient to changes in data distribution. One other method is data augmentation, which involves generating new training samples by applying various transformations to the original data, such as rotation, flip, and color changes. This increases the diversity of training dataset without collecting additional data. So, other examples or techniques to solve this problem is layer normalization. This normalizes the activations of neurons. The difference between layer normalization and batch normalization is that batch normalization relies on making mini batches and its statistics. It is more suitable for sequence networks such as recurrent neural network and small batch sizes. However, layer normalization this reduces internal covariance shift, ensuring that activations within each layer have a consistent mean and variance. Group normalization divides the channel of a layer into groups and normalizes each group independently. This is a middle ground between batch normalization and layer normalization, has benefits of both. Instance normalization normalizes each instance in batch separately. Okay. So we kind of know now what is covariance shift, which we were talking about. So this is the thing that I was learning based on the table that it gave me. I'm focusing on this keyword right now and let's study it. So yeah, this is the transformer architecture, the components of transformer model. We talked about self-attention mechanism on how it causes all words in sequence simultaneously, basically focusing on the attention of the most important and relevant ones wherever it might be in the sentence. It does this by using query key and value matrices. Relevance between words is calculated using scale dot product formula. Next, we studied about positional encoding. As transformers don't process input sequentially, positional encoding preserves word order by adding positional information to word embeddings. it uses sine and cosine functions. So, for example, if we have two sentences like he ate the apple and the apple ate he, notice how these both two sentences have the word ate in it, but as you can see, the word ate is in two different positions. So, if we use positional encoding, these two would be different. But if we don't use it, if we don't use positional encoding, then the model will consider both of these sentences as same because of the words and their occurrences, I believe. Next, we read about multi-head attention. This is about applying self-attention multiple times in parallel, with each attention head learning different linguistic patterns. When it comes to parallel processing, some heads might focus on syntax, while others might capture semantics, and both the syntax and the semantics are then concatenated for a better result. Mm, Feed forward layer. Feed forward is when your input travels to the output layer with learning features from each layer. So this consists of two fully connected layers with an activation function with this formula. So it looks something like this. This is input layer, there is hidden layer, and there is output layer. There are no loops or feedbacks. It's used for tasks like pattern recognition. Notice how each of the input neurons has a weight attached to it, as well as it sometimes has bias as well. And there are hidden layers, so you can see it flows from each of them to layer, and then hidden layer combines to get the output layer. Inputs, weights, weights and inputs are multiplied, bias is added. So there is multiplication and summation. We give it to the activation function and then we get an output. Yeah, so this is feed forward layers. Layer normalization. It stabilizes training by normalizing activations across features to reduce internal covariate shifts, which we just read about, and improve convergence speed. During training, this normalization prevents sudden changes, feature magnitude, making the learning process more consistent. Residual connections. Transformers implement residual or skip connections that allow information to bypass multiple layers, improving gradient flow and preventing information loss. These connections are especially crucial in deep transformer stacks, where they ensure original information remains intact and help mitigate vanishing gradient problems. So let's see how this looks like residual connections or skip connection. The information flow is simply without like one layer, without forward direction, without skip connection. But see how with skip connection you can entirely skip this entire layer and directly go from here to here. So that's the advantage, I think. Weight layer, activation layer, weight layer, activation function. So we can directly go from here to here. So we have input, we have layer 1, layer 2, and then x. So the output y is fx plus x. Normal skip connection used when dimension of x of and output are stacked is same. Linear projection on the skip connection such that dimension of x hash and output of stacked figure is same. Oh, okay. This is kinda different. Let's read this. Why are residual connections needed in transformer architecture? Residual connections are often motivated by the fact that very deep neural networks tend to forget some information of their input data set samples during training. This problem is removed or solved by summing the input x to the result of typical feed forward network. So this is input. We don't want it to forget some features from layers. So this is identity. It is directly going to the ReLU and summation. This entire block is x. So fx plus x summation and then passed on to the ReLU. On the other hand, it is also well known that transformer architectures have some residual networks, as the following picture elaborates. Let's see. This is our input and these are outputs. So this is input. I think this is encoder. This is decoder. So we have input and then we are making input embedding. This input embedding is input might be a sentence, then converting it into embeddings or numerical forms. And then each of them has a position attached to it on where it sits and has query keys and value pair. So this is encoder block and it uses self attention and identifies the most important word using the positions and also calculates the distance between each word and tokens. Queries, keys, and values are computed from encoder state. It has multi-head attention, addition, and normalization layers, feed forward layer, then addition layer. Feed forward network. After taking information from the other tokens, take a moment to think and process this information. So encoder takes all the info, extracts query key value. Feed forward layer takes a moment to think and process this information. So here you can see this line and then this line and then this line. These are all residual connections because it's like learning from earlier layers, passing it on. So we finished with the encoder block. Next, we pass this information to the decoder encoder attention block. So decoder encoder attention target tokens looks at the source. So queries are coming from the decoder states and keys and values are coming from the encoder state. Also, decoder has self-attention which is masked. Tokens look at the previous token. Query key value are computed from decoder states. After taking information from other token, it processes and gives it. Okay. Residual connections are motivated in the context of very deep architecture, but tension blocks perform very little computation. What is the motivation? The presence of shortcut connections in attention blocks. The reason for having residual transformer is more technical than motivated by architecture design. Residual connections mainly help mitigate the vanishing gradient problem. During the backpropagation, the signal gets by the derivative of the activation function. So as we move to minimize the loss during backpropagation, we are taking derivative of the activation function like ReLU or sigmoid. And in the case of ReLU, it means that in approximately half of the cases, the gradient is zero because ReLU looks like this. Like the gradient of zero would, like this, would turn zero, right? So we are almost dropping all the important info. Without the residual connections, a large part of the training signal would get lost during backpropagation. Residual connections reduce effect because summation is linear with respect to derivative. So each residual block also gets a signal that is not affected by vanishing gradient. Another effect of residual connection is that information stays local in the transformer layer stack. The residual connections, however, always remind the representation of what the original state was. Interesting. Okay. What I'm gonna do is I'm gonna ask. Okay, wait, if we can get an example. Example of residual low connection in a sentence, step by step. Okay, let's move on. Residual skip connections that allow information to bypass multiple layers, improving gradient flow and preventing information loss. These are important in deep transformer stacks. How does the transformer model work? The transformer model consists of an encoder and decoder, both built using multiple layers of self-attention and feed-forward networks. So, if we have an input, the input text is tokenized and converted into embeddings. Transformer example. Okay, we'll read this later. First, let's finish this. The input text is tokenized and converted into embeddings. The encoder applies multi-head self-attention and feed-forward layers. Residual connections reduce. Okay, so the encoder applies multi-head self-attention and feed-forward layers. The self-attention mechanism computes the most important word or attention using query key and value matrices. Then after self-attention, there is multi-head attention, where it's like parallelly giving scores. Then the output of different layers is passed to the feed-forward neural networks. This processes attention outputs within the encoder, and then we have decoder. Decoder uses encoder output and target sequence to generate predictions. Let's read. Input processing. The input text is tokenized and converted into word embeddings. Positional encodings are added to maintain word order information. Encoder. This takes input embeddings and applies multi-head self-attention. Utilizes positional encodings to maintain word order, passes information through feed-forward layers for processing. Then we have self-attention mechanism. The self-attention mechanism allows each word to focus on relevant words dynamically, computes query, key, and value matrices for each word, generates attention score using scale dot product attention. Then it applies softmax to normalize attention scores, weighting value vectors accordingly and summing them. So then we move on to the multi-head attention. So instead of a single attention mechanism, multi-head attention allows the model to capture different relationships within the input. And then this is passed to the feed-forward neural network from input to output. Now all the output from encoder is passed to the decoder. So decoder receives encoder output along with the target sequence. It uses masked self attention to prevent looking ahead. Combines encoder decoder attention to refine output predictions. So let's consider an example of English to French translation using transformer model. So this is the sentence: transformer are changing AI. If this is the sentence, first tokenization happens. So each of the words in the sentence is separated into separate words: transformers are changing and AI. So these are four tokens in this one sentence. Then we convert it into embedding. Transformers are changing AI. I'm sure this image is generated by AI. That is why the spelling is messed up. But it's okay, it's just to understand the concept. Next, this output and embedding layer is passed to the encoder. And now it encodes the position of words, less on AI, like importance of different words, and puts it here. Then multiple attention heads capture linguistic pattern and then decoder processes it. So there is something called start of sequence token. So if this is the start of sequence token, we can predict the first word for the transformer and use previous predictions to generate the next word. So the transformer in French stands for LES. Sorry, the word the stands for less in French. So it just changed this first and then it will use this prediction to guide the next word. So you can see it successfully did English to French translation from this sentence to this sentence. So our input sentence was transformers are changing AI. Words are tokenized into different parts. Each token is converted into a vector representation. Then positional encoding happens, encodes the position of words in the sequences. Then encoder self-attention happens. The model computes attention weights for each word. Example, transformers might have high attention on changing but less on AI. Multiple attention heads capture different linguistic patterns. The decoder starts with this token. It predicts the first word less for the transformers and uses previous predictions to generate the next word. This is the final translated sentence. These are the applications of transformer, the GPT architecture, BERT, and T5 model. Machine translation used in Google Translate and similar application. Text summarization enabling AI-driven summarization tools, speech recognition, enhancing voice assistants like Alexa and Siri. Computer vision applied in vision transformers for image processing. The advantages is parallelization. Unlike RNNs, transformer process input sequence simultaneously. Long range dependencies effectively captures relationship between different words. Scalability, easily adaptable to larger datasets and complex tasks. State of the art performance outperforms traditional models in NLP and AI. Challenges would be high computational cost, training complexity, and interpretability, like how transformer make decisions. Sometimes they need fine tuning as well. Okay, let's read FAQs. Why do transformer use multiple attention heads instead of just one? Transformer use multiple attention head to capture different aspects of word relationship. A single attention mechanism may focus too much on one pattern. Multiple heads allow data to learn various linguistic structures such as syntax and semantics. How do transformer handles very long sequences efficiently? While standard transformers have fixed length limitation, variants like long former and reformer uses like sparse attention, memory efficient mechanism without excessive cost. Hyperparameter tuning is a key challenge because it can forget in continuous learning. Okay, this was a really nice article, I believe. It's from Great Learning. And then we found another article on transformer. Let's read this one. This is from AWS. So, what are transformers in AI? Transformers are a type of neural network architecture that transforms or changes an input sequence to an output sequence. Early DL models focused on NLP to respond to natural human language. For example, autocomplete feature. The earlier ML model mapped different word pair and word groups in training dataset and tried to guess the next word. However, it wasn't possible after a certain input length because although it was able to predict the next word, but it wasn't able to generate meaningful paragraph and could not retain the context or details between the first and last sentence in the paragraph. So then transformers came into picture, and these process long sequences with parallel computation. This is the root of LLMs such as GPT and BERT that can learn complex language representation. This also enables multimodal AI systems such as models like DALI can generate images from text, combining natural language processing and computer vision. With transformer models, you can use techniques such as transfer learning and retrieval augmented generation. These techniques enable the customization of existing models for industry organization specific applications. Model can be pre-trained on large dataset and then fine-tuned on smaller task-specific dataset. This approach has democratized the use of sophisticated model and removed resource constraint limitation. Training large models from scratch. What are the use cases of transformers? NLP, machine translation, DNA sequence analyzer. Segments of DNA as sequence segments similar to language. It can predict the effect of genetic mutations, by understanding genetic patterns and help identify regions of DNA that are responsible for certain disease. This is nice thing for personalized medicine, where an individual's genetic makeups can lead to nice treatments. Protein structure analysis. Transformer models can process sequential data, which makes them well suited for modeling long chains of amino acids that fold into complex protein structure. Understanding protein structure is vital for drug discovery and understanding biological process. So it uses encoder decoder architecture pattern. Encoder reads and processes the entire input sequence, such as English sentence, and transforms it into a compact mathematical representation. This representation is a summary that captures the essence of the input. Then the decoder takes the encoder input and step by step generates the output sequence, which could be the same sentence translated into a different language. Self attention. Transformer models modify this process by incorporating something called a self attention mechanism. Instead of processing data in order, the mechanism enables the model to look at different parts of the sequence all at once and determine which parts are most important. Imagine that you are in a busy room and trying to listen to someone talk. Your brain automatically focuses on their voice while tuning out less important noises. Self attention enables the model to do something similar. It pays more attention to the relevant bits of information and combines them to make better output predictions. And this is why the models like transformers are more efficient, because we can train them on large data set and it can successfully extract what are the necessary important features. Now let's look at the diagram of transformer architecture once again. It has different software layers that work together. Input embedding, positional encoding, multi-head attention, feed forward. This is encoder block. This is decoder block. Then we have output embedding and the output probabilities as well. So let's read about this input embedding layer. This stage converts the input sequences into mathematical domain that software algorithms understand. At first, the input sequence is broken down into a series of tokens or individual sequence components. For instance, if the input is a sequence, then the tokens are words. Embedding. This embedding then transforms the token sequence into a mathematical vector sequence. The vectors carry semantic and syntax information represented in numbers, and their attributes are learned during the training process. Okay, so moving on. This input embedding can be visualized. We can visualize vectors as a series of coordinates in an n-dimensional space. As a simple example, think of 2D graph where x represents the alphanumeric value, the first letter of the word, and y represents the categories. So imagine if the word banana, it has value 2 by 2 because it starts with the letter B and is in the category fruit. The word mango has the value 13, comma 2 because it starts with letter M and is also in the category fruit. In this way, vector xy tells the neural network that the words banana and mango are in the same category because their y value is same. So they are both in the category of fruit. So that's how when you give a sentence and it gets converted into tokens and then converted into embeddings, then a mapping happens in the 2D space. The embedding converts every sentence into numerical representation and tries to map it in different categories. But this is easy because it's just two words and few categories. But imagine an n dimensional space where we have thousands of attributes about any words, grammar, meaning, and sentences mapped to a series of numbers. So, software can use the numbers to calculate the relationship between words in mathematical terms and understand the human language model. Embeddings provide a way to represent discrete tokens as continuous vectors that model can process and learn from. Positional encoding is a crucial component in the transformer architecture because the model itself does not know and process sequential data in order. So the transformer needs a way to know the order of the tokens in the input sequence. Positional encoding adds information to each token's embedding to add its position in the sequence. So we have token, and with each token we have its position as well. So if I know he ate the apple is a sentence, I know he has position 1, ate has position 2, the has position 3. So we are adding it. That's how it knows. How is it done? This is often done by using a set of functions that generate a unique positional signal that is then added to the embedding of each token. With positional encoding, the model can preserve the order of tokens and understand the sequence context as well. A typical transformer model has multiple transformer blocks stacked together. Each transformer block has two main components: a multi head self attention mechanism and a position wise feed forward neural network. The self attention mechanism enables the model to weigh an importance of different tokens within the sequence. It focuses on the relevant parts of the input when making prediction. So, as you can see in the diagram, each of them has a multi-head attention and a feed forward layer, just as it is mentioned. Let's consider the sentences speak no lies and he lies down. Both have different meanings. In both sentences, the meaning of word lies cannot be understood without looking at the word next to it. So even though this is same but has different meaning, but its real meaning is generated due to the words which are beside it. The words speak and down are essential to understand the correct meaning. So, self attention enables the grouping of relevant tokens for context. The feed forward layer has additional components that help the transformer model train and function more efficiently. Each transformer block include connections around the two main components that acts like shortcuts. They enable the flow of information from one part of the network to other, skipping operations in between. These are called residual connections that we read about earlier. So you can see it allows you to skip information. So information can go from here to here directly, or from here to here to here directly instead of going through every part. We have lower layer normalization that keeps the numbers outputs different layers in the network. Linear transformation functions so that model adjusts value to perform the task. So lean down. Okay, this is for transformation. Like if you want to have translation or summarization, so it's different for different types of output we want to have. Uh, we can see here we have linear and softmax activation function blocks. Ultimately, the model needs to make a concrete predictions, such as predicting or choosing the next word. If I'm typing a word in my phone, it shows the next word, right? So it's making a prediction. This is where the linear block comes in. We have a fully connected layer, also known as dense layer, before the final stage. It makes a linear mapping from vector space to the original input domain. And output of this is a layer of scores, often called logits, for each possible token. The softmax function is the final stage that takes the logit scores and normalizes them into a probability distribution. Each element of softmax output represents the model's confidence in a particular class or token. Let's read it again. The softmax function is the final stage that takes the logit scores and normalizes them into a probability distribution. Each element of the softmax output represents the model's confidence in a particular class or token. Okay, this looks like pretty interesting. It talks about how are transformers different from other neural network architectures. As far as I know, CNN or convolutional neural networks are used for image based applications, whereas RNN or recurrent neural networks are used for um, a sequence based applications or time series. Um, so transformers use RNNs as both for processing sequential data. Yeah, we were right. RNNs process data sequences one element at a time in cyclic iterations. The process starts with the input layer receiving the first element of the sequence. The information is then passed to a hidden layer which processes the input and passes output to the next time step. This output combined with the next element of sequence is fed back to the hidden layer. And this cycle repeats for each element in the sequence, with RNN maintaining a hidden state vector that gets updated at each time step. This process enables RNN to remember information from past inputs. So let's see RNN architecture. What is this? Recurrent theory, and every ant is independent variable and goes in different directions. Order of ant matters. RNN has following models: one to many, one input, and generates a sequence of words. So one to many, many to one. Review, sentiment analysis. Many to many. मैं तेनू प्यार करदा. Love you. Takes. This movie was not input. So we have hidden layer. Okay, I know that. RNN cell consists of set of feed forward networks because we have time steps known as sequential input, sequential output, multiple time steps, and multiple hidden layers. So multiple inputs, multiple outputs, multiple hidden layers. Here we calculate hidden layer values not only from input but also previous time steps. Not only just from input but also from previous time steps. At time steps t, this is the formula, then this. In the picture we are calculating hidden layer time step to activate, then softmax. This is sigmoid formula, tan h and ReLU. Then is also back propagation through time. How much does the total error change with respect to output? Which does output change with respect to weight? Back propagation for RNN is same as neural networks back propagation. But here current time step is calculated based on previous time step, so we have to traverse all the way back. We apply chain rule. Okay. Similar, take the derivative, summation it, and then chain rule. dE by dt. This cancel out, this cancel out, this cancel out. This movie is not good. We give word vectors or one hot encoding vectors for every word input. And we do feed forward and BPT. Okay, that was nice. I'm gonna clap for him from my real Medium account. This is my Medium account. Here RNN, it's like this. In LSTM we have hidden gate, forget gate, I think. Oh, what is the main difference between RNN and LSTM? The main difference between RNN and LSTM is in terms in which one maintain information in memory for a long period of time. LSTM has an advantage over RNN. So LSTM can handle information memory for long time. Question is, what is? Oh, this was a question I thought. Deep learning models have taken the world by storm, revolutionizing field image recognition, speech synthesis. This is GRU. A gated recurrent unit is type of ANN structure that is used for processing sequential inputs such as speech, text, or sensor. It has memory capabilities that allow it to remember important details across time steps, decide whether to pass them forward or discard them. This is reset get, update get. Kinda reminds me of control systems, which I studied back in my electronics course. I think, yeah, control systems, get. Electronics. Was it? control systems, or which subject was it in? Okay, I'll get this later. GRUs can be particularly effective in analyzing long range dependencies between input, making them useful for various industrial applications. Oh shit, this is logged. Wait. Gonna open it here. Yeah, it's still logged. कोई बात नहीं. In contrast, transformers process entire sequence simultaneously. This parallelization enables much faster training times and the ability to handle much longer sequences than RNNs. The self-attention mechanism in transformer also enables the model to consider the entire data sequence simultaneously, eliminates the need of recurrence or hidden vectors. Instead, positional encoding maintains information about the position. Transformers have superseded RNNs in many applications, especially in NLP tasks, because they can handle long-range term dependencies more effectively. They have greater scalability and efficiencies. CNNs are designed for images where spatial hierarchy and locality are key. They use convolutional layer to apply filters across input, capturing local patterns through these filtered views. What are different types of transformer models? Transformers have evolved into family of architectures. Bidirectional transformers. Bidirectional encoder representations from transformers. BERT models modify the base architecture to process words in relation to all other words in a sentence rather than in isolation. It employs a mechanism called the bidirectional masked language model (MLM). During pre-training, BERT randomly masks some percentage of input tokens and predicts these masked tokens based on their context. The bidirectional aspect comes from the fact that BERT takes into account both left to right and right to left token sequences in both layers. How does it look like? BERT is a language model introduced in October 2018 by Google. Text as sequence of vector. I didn't know it had a face. But Google. Architecture. So transformer has encoder and decoder. GPT is just decoder. BERT is just encoder. So transformer is combination of BERT and decoder. Okay. BERT explains state of art model for NLP. Bidirectional encoder representation from transformer is a recent paper published by researchers at Google AI Language Lab. It has caused a stir in ML community by performing good in question answering and natural language inference. BERT's key technical innovation is applying the bidirectional training of transformer, a popular attention model, to language modeling. This is in contrast to previous efforts, which looked at a text either from left to right or from left to right or right to left. This results show that a language model which is bidirectionally trained can have deeper sense of language context and flow in a rather than single language directions. The field of computer vision researchers have repeatedly shown the value of transformer learning. Pre-training a neural network model on a known task, for instance ImageNet, and then performing fine-tuning using the trained neural network as basis of a new purpose-specific model. In recent years, researchers have been showing that a similar technique can be useful in many language tasks. BERT BERT makes use of transformer, an attention mechanism that learns contextual relationship between words or subwords in a text. In its vanilla form, transformer includes two separate mechanisms: an encoder that reads the text input and a decoder that produces the prediction for the task. Since BERT's goal is to generate a language model, only the encoder mechanism is necessary. The detailed working of transformer is in a paper by Google, as opposed to directional models which read the text input sequentially from either from left to right or right to left. The transformer encoder reads entire sequence of words at once. Therefore, it is considered bidirectional, though it would be more accurate to say that it is non-directional. And this allows to learn the context from all its surrounding left and right of the word. When training language models, there is challenge of defining a prediction goal. Many models predict the next word in the sentence. For example, if our sentence is the child came home from dash and you have to predict the next word, a directional approach would be inherently limiting context learning. Like it might be some place. So BERT uses two training strategies. First is masked language model. Before feeding word sequences into BERT, 15% of words in each sequence are replaced with this token mask. So in a sentence uh, we try to hide it via via this token. The model then attempts to predict the original value of the masked word based on the context provided by other non-masked words in the sequence. We have to add a classification layer on top of encoder output. So input, embedding layer, encoder, output, classification layer. Then we multiply the output vector by embedding matrix, transforming them into vocabulary dimension. and we calculate the probability of each word with softmax. The BERT loss function takes into consideration only the prediction of the masked value and ignores the prediction of non-masked word. As a consequence, the model converges slower. In the BERT training process, the model receives a pair of sentences as input and learns to predict the second sentence in the pair is the subsequent sentence in the original document. During training, 50% of inputs are paired with the second sentence is the subsequent sentence, while other 50% is a random sentence. To help model distinguish between two sentences, input is processed in the following way. A CLS token is inserted at the beginning of first, the SCP at the end of each sentence. Sentence embedding indicating sentence A or sentence B is also added to each token. A positional embedding is added to each token to indicate its position. So if this is the input, my dog is cute, he likes to play, he likes playing. So you can see we added the CLS token at the beginning and a SCP token at the end. And then we make it into embeddings like ECLS, embedding of my, embedding of mask, so follows. Then we have sentence embedding like this belongs to sentence A, this belongs to sentence B. Positional embedding is added to each token to indicate the position in the sequence. To predict if the second sentence is indeed connected to the first, the following steps are performed. The entire input sequence goes through the transformer model. The output of CLS token is transformed into 2x1 shaped vector using classification layer. We calculate the probability of is next with this. So how do we fine tune it? What can be used for a variety of wide language tasks. Classification tasks such as sentiment analysis are done similarly to next sentence classification by adding a classification layer on top of transformer output. In question answering tasks, for example, Squad, the software receives a question regarding a text sequence and is required to mark the answer in the sequence. Using BERT, a Q&A model can be trained by learning two extra vectors that mark the beginning and end of the answer. In named entity recognition, the software receives a text sequence and is required to mark different types of entities, person, organization, date that appear in the right text. Using BERT, NER model can be trained by feeding the output vector of each token into classification layer that predicts NER label. Model size matters even at huge scale. With enough training data, more training steps gives higher accuracy. BERT's bidirectional approach converges slower than left to right approaches. So we now have a small idea about BERT. GPT. Let's talk about GPT. GPT stands for Generative Pre-trained Transformer. Use stack transformer decoders that are pre-trained on large corpus of text by using language modeling objectives. They are autoregressive, which means they regress or predict the next value in sequence based on all the preceding values. By using more than 175 billion parameters, GPT models can generate text sequences that are adjusted for style and tone. GPT models have sparked the research in AI towards achieving artificial general intelligence. This means that organizations can reach new levels of productivity while reinventing their applications and customer experiences. A bidirectional autoregressive transformer is a type of transformer model that combines bidirectional and autoregressive properties. It's like a blend of BERT's bidirectional encoder, GPT's autoregressive decoder. Reads the entire input sequence at once and is bidirectional like BERT. However, it generates the output sequence one token at a time, conditioned on the previous generated tokens. Transformer for multimodal task. Multimodal transformer models such as Vision Language BERT and Visual BERT are designed to handle multiple types of input data, specifically text and images. They extend the transformer architecture by using dual stream network that process visual input separately before fusing. This enables to learn cross-modal representation. Wilbert uses co-attention transformer layers to enable separate streams to interact. It's crucial for situations where understanding the relationship between text and image is the key, such as visual question answering tasks. Vision transformers repurpose the transformer architecture for image classification. Instead of processing an image as grid of pixels, they view image as sequence of fixed size patches. Each patch is flattened, linearly embedded, and then processed sequentially. In AWS, we have Amazon SageMaker, Amazon Bedrock, used by these startups with a single API. Tranium. Okay, this is nice. Done with this. So now we have an idea of feed-forward neural network, BERT, NLP, basics, covariant invariance, transformer, GPT, BERT, transformer, BART, multimodal, and things like that. Okay. Okay, I'm gonna take a break for a while and then maybe I'll resume this in the next video. This video was about transformers mostly and just high level revision. Maybe I'll study for next topics in few hours. Yeah, that will do, I think. I was able to revise so many concepts. I think I studied them for maybe 2-3 months back, but it was a nice revision. I'll maybe make another video in another next hour or something. Study for the next part. This was fun. Thank you for joining. Peace out.